Now, f and a, does that exist?
No.
No. No. So you can have a scenario where the left-hand side is a real limit. It exists as finite quantity, but the right-hand side does not exist. And so therefore, is this function continuous at a? No. And it conforms to what you expect geometrically. If you're drawing this thing, you must lift up the pencil and start over again, therefore not continuous from the more simple pre-calculus definition. Okay? Now, I'm just going to stick with the same picture for a quick second. So I'm going to now write this up here. Okay. So now, what changes about the scenario? Does the limit of f of x as x approaches a exist, according to this picture now? Yes, it's that location right there, right? The limit exists. Does f of a exist?
Yes.
Yes, it does. So now you have both the left and the right side existing, right? These two things both are finite quantities. But what's the problem?
It's not
the same. The third part fails. Not the same. So therefore, is this thing continuous at A? No. Again, the way you draw it, you have to lift up, dot there, start again. It conforms to what you think of when you think of your pre-calculus definition. Is that okay so far? Why they're failing to be continuous at the moment. Another example. There's f of x now. So, and this is what we'll call a. I guess a is 0 at the moment. So does f of a exist? Yeah, there's a little dot there, right? I don't know what it is. There it is. 1. We'll say it's 1 for good old time's sake. 0 to 1. F of a is 1. F of a exists. The right-hand side exists. Does the left-hand side exist? Does the limit of f of x as x approach a exists? No. D and E. I don't even care about the third part now. They can't equal if one of them doesn't exist. So again, it conforms to your understanding, right? Since the limit doesn't exist, the definition fails. F is not continuous there. Why? In this case, it's an asymptote. That's why. You have to draw, lift up, start again on the other side, right? Those are three basic cases of why it will fail to be continuous at a point. So you need all three things in play. Limit existing, the function existing there, and they are the same thing, and then it is continuous at that one location. Any questions so far? Any questions so far? Let's try a problem. Number 15. And it's a little more subtle now. Just working with this definition. You got the definition memorized? I'm just going to erase it. You got it memorized, basically? Good. Good deal. This is a good memory. We're going to start with this function. It's x. This is number 15 in this section. F of x is a piecewise defined function. X squared minus 1 over x minus 1. And 3, depending on what location you're at. Is that right? Okay. That's the definition of the function we're supposed to deal with. It's kind of complicated already. It's a piecewise defined function we haven't really talked about so much yet. You're supposed to know it from pre-calc, but it may have been a while. And now we want to examine, is this ridiculous looking thing, f of x, continuous at a equals 1? That's the question the book poses. Right? A equals 1? Otherwise, not much to talk about that. Right. Is this thing continuous at 1? Right. So we need to make sure the three parts of the definition hold up. That the limit exists for this function at 1. The function exists at 1. And those two things end up being the same quantity. Yeah?
The nature of a piecewise function.
Say it one more time.
The nature of a piecewise function.
Not necessarily. Piecewise defined functions, usually that is the way it works. And that's why we have them most of the time. Right? But you could have something as simple as, it's like a quadratic, and then it acts like a line right there. But they do actually connect that one location. Most piecewise you think of, well, it starts over here and does something like that, right? But they can connect at their connecting point, right? It's possible. and likely if the book wants you to find an answer to the problem. All right, so continuous or no? So we have to examine the limit of the function as x approaches 1. We need to figure out what the function is at 1, and then make sure they're the same. And if any one of these three things fails, just immediately say it's not continuous there. Got it? Okay, let's do the limit first. Limit of f of x as x approaches 1. All right. Is x ever going to be 1 in this limit? Nope. Never going to be 1. So therefore, which part of this function am I dealing with? The upper part or the lower part? What's that? No, I'm doing that part. Since x will never be 1, I'm dealing with all the x's that are not 1.
Oh.
That's all right, whatever. You know what I'm saying? So I'm dealing with this part. I'm dealing with everything around 1. You meant the upper?
I meant the denominator.
Oh, denominator? Oh, no, sorry, I meant upper and lower, not really proper. Where is it? I meant upper here and lower there is what I meant.
Oh, I thought you meant numerator.
Yeah.
The fresh.
All right, sorry. All right. So what I was trying to say was we were dealing with the first part of this piecewise, the first piece of this piecewise defined function. We're dealing with that, right? Because being 1 is not an option for this limit. So I don't care about the 3 right now, right? I'm dealing with everything where it's not 3. All right. Now, can you tell me what that limit is? 3. Knocked that one out of the park. 3 just called out 2 like nothing. Everybody agree? 2? Yeah? Doesn't matter which side either, right? This is the first problem we did, isn't it? This is the first limit we ever did, isn't it? That's, those are the times, right? Those are good days. Yesterday. All right, whatever. It's 2. Okay? It's 2. So we now know the limit as x goes to 1. All right? So now I need to know what is f of 1. What is it?
3.
Right. 3. It's 3. The function itself tells you, right? 3. All right. So the limit exists. It's a finite value. It's called 2. The function exists there. It's called 3. But they are not the same. So therefore, it fails to be continuous at 1. F is not continuous at x equals 1. Not. Okay so far? Who can tell me what the picture looks like? Looks like a line with a... Where's the hole? At 1.
Yep.
What's the height of the hole?
1, 2.
Right. So it looks like that. It doesn't really hook like that. So it looks like that sort of. And over here at 1, there's a hole. And that hole height is 2, approximately. But what's the function at 1? It's actually higher. Right. It's actually here at 3, and it's filled in. So that is the picture we're talking about right now.